Hello everyone. Today we'll be talking about derivatives, but before we do that, let's talk about these things called secant lines. So if I have a function, maybe it looks like this, then I choose maybe an a here, and then this would be my f of a down here, and then maybe I choose another point b right here, and then this would be my f of b. Then what I can do is I can form something called a secant line between these 2 points on the function. So here, right? So a secant line is really just a line formed between 2 points on a function. And because it's a line, I can find out the equation of that line using point-slope form. So then the equation is going to be y minus f of a equals the change in y, which will be f of b minus f of a, over b minus a times x minus a. So this just comes from point-slope form. And yeah, here we go. And it actually turns out that the thing that we're interested in is the slope here. When it's a secant line, it's called an average rate of change of the function from a to b. And this is the formula, the change in y over the change in x. So really kind of simple stuff here. But now, if you had a good pre-calc teacher, you normally see this in pre-calc. But now we're going to imagine moving this b closer and closer to a. So maybe now here's my second b, and then my new secant line maybe looks something like this, right? And then now maybe I've got a third b down here, and then maybe now it looks something like this, right? And then now I keep getting closer and closer and closer and closer. Eventually what's going to happen is that they're going to become the same point. So A and B are going to coincide the same point, and you get something called a tangent line. And if you look at it on the graph, yeah, sure, it makes sense. I can imagine a line right there. Nothing like destroys itself. But if you look at the formula, well, f of a and b are the same thing. So f of a and f of b should be the same thing. So f of b minus f of a should be 0 because they're the same. And then again, divided by b minus a, they're the same thing. So we get 0 divided by 0. That doesn't work. In all the math that we've had up till now, we've never been able to do 0 divided by 0. So this is kind of interesting, where in the graph we get this cool line called a tangent line, but in the formula something goes horribly wrong. So how do we resolve this? It turns out that that's the entire point of why we have limits. So we're going to define the derivative of f. We write it f prime of x as the limit as b approaches a of f of b minus f of a over b minus a, right? Okay, so again, what we were interested in from the last screen was just the slope of it. We just want the slope of it, and this limit right here as b approaches a is going to help us resolve the 0 divided by 0 issue. And actually, in a lot of cases, we'll see that this limit actually exists, even though you can't just plug in b equals to a. But in order to make this look more like the definition of a derivative you'll see in textbooks, we're going to change something. Let's change this b to an x. Just because we want this to be a function of x, We could have called it x the whole time, but it would have been a little bit confusing. Now this makes sense. This is the formal definition of a derivative, and then we can write it equivalently as saying f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over, it would be x plus h minus x, which is just going to simplify to h. So then let me convince you that these two things are the same thing. If I go back to our function, here I'm going to choose this to be an x, and here x is not like a variable here, it's a fixed value. It's sort of playing the role of both. And then here, this is my x plus h, and then the distance between these is h. So then I take my point and I make the distance between them. Again, we can think of it as coming from both sides, right? So h can be negative, but I'm bringing my x plus h really, really close to my x, and so my h goes to 0. So this is the definition of a derivative. And it turns out that this is a incredibly useful thing to know. We say that a function f of x is differentiable at a point A if f prime of A exists. So what does f prime of A look like? It's going to look like, you just put A in the formula. This is just my personal bias. I happen to like this formula a lot more than this top one. It just turns out to be a little bit more versatile and useful. So I'm going to write the limit as h approaches 0 of f of A plus h minus f of A over h. So if this limit exists, then we say that the function f of x is differentiable at the point A. And if it's differentiable at every point in an interval, then we say that it's differentiable on that interval. Sort of like the same thing we saw with continuity. If it's continuous at every point, then we say it's continuous. If it's differentiable at every point, then we say it's differentiable. Okay, so now that we have the definition out of the way, let's start with the theorem. If f is differentiable at A, then what? We know it's continuous at A. Then f is continuous at A. And this might be hard to grasp intuitively, so let me go through the proof first and then try to explain it with a graph. So then we want to show that it's continuous at A, so we have to show that the limit as x approaches A of f of x is equal to f of A. And an equivalent way of writing this is we need to show that the limit as x approaches A of f of x minus f of A, we want to show that this thing is equal to 0. So I've just moved the f of A to the left-hand side and then brought it inside the limit, and we're going to show that this thing is equal to 0. Well, first, notice that this thing is certainly equal to f of x minus f of A divided by x minus A, and then we can times it by x minus A as well. So essentially I'm just multiplying and dividing by 1, and Here we're thinking of x as something different than a. And then if I take the limit of both sides of this f of x minus f of a, this is going to equal the limit as x approaches a of our quotient and then times, I'm going to write it suspiciously over here because the next step is to remember that the product of the limits is the limit of the product. So I can do multiplication inside or outside. So that means I'm going to distribute this limit right here, and I can also write it again right here. Okay. Well, then now what does this mean? Well, this limit, the left one, or the limit of the quotient, that's just the definition of the derivative at a. So we needed that f was differentiable at a in order for this to make sense. So this is going to be f prime evaluated at a. Okay, and then what is the limit as x approaches a of x minus a? Well, you can just plug in a here and you'll get a minus a, that's times 0, and then you'll get equals 0. Cool. So if x is not differentiable, then we can't say anything about its continuity at all because this quotient doesn't exist. So what does this look like on a graph? Well, imagine you had a function that wasn't continuous. Imagine you had something like this, right? So it's continuous everywhere except for this little jump. If I tried to draw tangent lines, imagine this is like a tangent line at that point. Imagine this is like imagine that's a tangent line at that point, right? I'm really bad at drawing these, but I think you get the point. If I approach here, right, I'm going to get one tangent line. And then if I approach here, I'm going to get another tangent line. Maybe I can draw a better example. Here's a better example. Maybe I'm going to come down like this, and then I jump, and then I go up, right? So now we're asked, again, the only thing we really care about is the slope of these. So the slope of all these lines that I'm drawing right now is obviously negative. So if I come to this discontinuity from the left, it's going to be negative. If I come to the discontinuity from the right, the slope of all these tangent lines is positive. So if it's discontinuous, then we can't, it's definitely not differentiable. Maybe, in some cases where it's like, right here, this is a famous function, then it's 0 from both sides, right? And then maybe you can argue like, hey, it doesn't, of course it's not going to be differentiable at that point because it's not continuous, but maybe you can just fill in the gap. But in general, if it's not continuous, then we definitely can't say that it's differentiable. But if it's not differentiable, then it could still be continuous or not continuous. An example of a function that is continuous but it's not differentiable is the absolute value function. So what does this look like? It looks like a v, right? So if I imagine what's the slope of all these tangent lines here, well, this is just going to be -1. And then what's the slope of all these tangent lines here? It's going to be +1. But then here, at this point, I can draw tangent lines with whatever slope I want. I can draw it with 0. It's only going to touch that point. I can draw it with 1/2. I can draw it with -1/2. So it's not differentiable at what we say are sharp points. So if it's got something like this, that point right there is not differentiable. So differentiable implies continuity, but continuity does not imply differentiable. Okay, great. So now that we have that theorem, let's talk about just some ways that we write the derivative. This way of writing it as f prime is super common. You see it all over the place. There's another way that we write it. It's sort of with this fraction of like a differential with respect to f divided by a differential with respect to x, and this kind of comes from the idea that we're making it's like rise over run, right? We're making a very small change in x divided by a very small change in, a very small change in f divided by a very small change in x. And you've probably seen this symbol before over. So this is a capital letter delta. It means change in, but it sort of means like finite change in. When we use the letter d, we're thinking about an infinitesimal change in. So kind of going back with the epsilon delta thing where we're thinking of them as like infinitesimally small numbers, this d we're thinking as an infinitesimally small change in. Okay, so that's two ways you'll see the derivative written. They mean both the same thing. They mean the derivative. Another way that you'll see it is, say you have like y as a function of x, right? Then the derivative with respect to y, you might see it with a dot over it. This is normally used a lot in physics, especially when you're talking about functions like position, velocity, acceleration. Before calculus, if you wanted to describe any of these things, you'd have to use this this symbol right here, and you'd only be able to talk about average changes over time. Like if I had a car that went like 300 miles over, say, well, maybe not 300 miles. Maybe I had a car going 60 miles over an hour. Well, what speed would that car be going? It's distance over time, but it's an average distance over an average time. So that car would be going 60 miles an hour. So this symbol right here, you'll see with the dot, you'll see a lot in physics, but normally at higher level physics, it's reserved for specifically when the function is taking a time derivative. So here in pure math, we don't really worry about time a lot because it's a physical thing, but in physics they have to. So they have a special function, they have a special notation for when you take a specifically time derivative. So if I were to track position divided by time, right? Average position over average time, this would give me an average velocity. But if I wanted to take an infinitesimal change in position over an instantaneous change in time, that would give me an instantaneous velocity. And same thing with velocity. If I were to take an instantaneous change in velocity over an instantaneous change in time, that would give me an instantaneous acceleration. So sort of once you get into calculus and you learn about these things, derivatives, you learn that essentially velocity is the derivative of position, acceleration is the derivative of velocity, and kind of your life gets a lot more easier. Having to take average changes in everything just really limits you towards being able to calculate these things and really use these things in problems. But in general, these are the three ways that you'll see the derivative written. The top two are way more common than the bottom one, but the bottom one still has its use. And then if we can take the function, if we can take the derivative of a function, can we take the derivative of a derivative? What would that even look like? Well, the way that we write it is we'll write df dx, and we know that this means the derivative, and then we'll apply a ddx on it. So Just like how a function can be applied onto inputs, we're thinking of this might be a new term, we're thinking of this as an operator applied onto a function. So this derivative is a function. It's the function that gives the slope of the tangent line at every single point on your function. And then if you want to take the derivative of that, this is what's called the second derivative. We write it as d squared f over dx squared. And you might ask, well, why is the square not on the f? Why is it on the x? And those are good questions. The answer is sort of just, that's how the notation is. But the second derivative is very interesting. Again, it's the acceleration when you're thinking of your function as position. But if you're not thinking of your function as just position, it's just any regular old function. When the first derivative is positive, that means that you're going up, right? Your tangent line is positive. When it's negative, that means you're going down. When your second derivative is positive, that means you're what we call concave up. It means that you're in this like bowl shape. So this point right here, we consider concave up. If your second derivative is negative, then you're in this like cap shape. Yeah, it's sort of like a right side up bowl versus an upside down bowl. And this point right here is called the point of inflection. It's just the name that we've given it. It's where you go from being concave up to concave down, or going from concave down to concave up. It's where you switch. And then we've also given these points to where the first derivative is equal to 0. We call them critical points. You can get more specific about calling them maxes or mins, and we will see that soon enough, but these are called critical points. So what does this all mean? This means that if you know a function, you know information about it, you know information about its derivative, you know information about its second derivative, you've actually got a pretty good shot of accurately drawing the function. So you know where the second derivative is positive, negative, or 0, that's going to force what the graph is going to look like. If you know where the first derivative is positive, negative, or 0, that's going to influence what the graph is going to look like. And then, of course, if you know where the function itself is positive or negative, being above or below the x-axis, that's obviously going to influence what the graph is going to look like. So there's a lot of problems on just graphing based on what information you know about the derivatives or so. But yeah, so this is the second derivative. If you wanted to write a higher order derivative, you just write d to the n f over dx to the n. Why do you have to stop at 2? Of course, you don't have to stop at 2. You can keep going if you want. But the more you go, the higher the exponent will have to be. And to end off this video, let's start with the first of 4 major rules when it comes to derivatives, something called the power rule. So if I have my function x to the n, and I want to take its derivative, it turns out that this is equal to n times x to the n minus 1. So the way to remember this is the power just comes down, and then it gets multiplied here, and then you just do minus 1 on the power, and then that's your new power. Okay, so let's actually prove this. And one stipulation that we'll have in this proof is that we need our power to be a natural number. So just a positive whole number. So the rule does work when you consider fractions and negative numbers, but that's a more complicated proof that we'll get into a little bit later. So if I were to take a derivative on x to the n, I'm going to plug that into my definition. This is going to be, this is going to be the limit as h approaches 0 of x plus h to the n minus x to the n over h. Okay, and then x plus h to the n, well, that's actually just a binomial. And from the binomial theorem, we know how to expand this. This is going to be the limit as h approaches 0 of the sum from when I equals 0 to n of n choose I times x to the n minus I times h to the I. And then we still have our minus x to the n, that didn't go anywhere, and we also still have our divided by h. Okay, so then let's think about the I equals 0 term in this sum. If I think about the I equals 0 term, I have n choose 0 times x to the n minus 0, that's just going to be x to the n, times h to the 0, that's just going to be 1, so that goes away. And then we have to ask ourselves, what is n choose 0? Well, that's just 1. How many, if you have n objects and you want to choose 0 of them, there's only one way to do that. You just don't choose anything. And so this is going to be 1 times x to the n, which is just going to be x to the n. Another way you can remember that is by remembering Pascal's triangle. Anything choose 0 is just 1. So this is important because we get x to the n for the I equals 0 term, but we're minusing an x equals n. So then these two are just going to cancel out. So then what this means is that I get the limit as h approaches 0 of the sum from when I equals 1 to n of n choose I of x to the n minus I times h to the I. But then I've already canceled out my minus x to the n, so then this is just divided by h. Okay, so now what's the next step? The next step is to cancel one of the powers of h here. So then this is going to be the limit as h approaches 0 of the sum from when I equals 1 to n of n choose I times x to the n minus I times h to the I minus 1. Great. So then we have to think we're sending h to 0, right? H is getting extremely, extremely small, basically 0. And, well, we're not running into any problems, right? Dividing by 0 or having a negative under the square root. So there's really no problem with me just plugging in 0 in for h. And in fact, when you do that, all of the terms except for 1 are going to vanish. Which term is that? That's going to be the I equals 1 term. So when I equals 1, this is h to the 1 minus 1, that's h to the 0. And when I put in h equals 0, I get 0 to the 0. Wait, hold on, that's a problem. But it's actually not, because we're thinking of h as not being exactly 0. We're thinking of h going to 0 or getting extremely arbitrarily close to 0 as we like. So this is not actually a problem. It's just a really small number to the 0 power, which is still just 1. So the only term that survives here is the I equals 1 term. All the other terms are being multiplied by 0. So then this is going to turn out to be n choose 1 times x to the n minus 1. We're almost there. We just have to remember what n choose 1 is. If we have n objects and we want to choose one of them, how many different ways is that? Well, that's just n. We can choose the first one, the second one, the third one, or we could choose the nth one, you know. So then this is going to be n times x to the n minus 1. Great. So we've proven our formula. That's really good. And we still have this stipulation that n has to be a natural number, but we'll see in a couple videos that that is not the case. The reason why I had to include this here is that you can't have the fraction as the top of a sum. You have to have a positive whole number as the top. And so that sort of restricts what we can do here, but we'll get another proof of it that sort of expands this and really kind of blows this out of the water. So now there are there's two corollaries to this. The first one is that if I want to take the derivative of a constant, right? Well, from the graph, this is just going to be a horizontal line, right? And I know that the slope of this horizontal line is 0. So I'm thinking in my mind this should be 0. But let's just go through it. Let's think this is really the derivative of c times x to the 0. And if I can pull the constant out, which means that this is just c times the derivative of x to the 0. And I didn't prove that, I didn't prove that 0 works here as the power. But you can look at the graph and sort of see, oh, the slope of this should be 0, or this, you can trust that this will be 0 times x to the minus 1, which is just going to be equal to 0. So the derivative of a constant is 0. That shouldn't come to a surprise, but something else that this implies is that the derivative of any polynomial, just polynomials are really good to take derivatives of. So if you have the derivative of, say, the sum from when I equals 0 to n of a to the I, or ai times x to the I, like this. So this is the form of a polynomial, and we're taking the derivative of it. Because, well, I guess I haven't gone over some of the rules yet. I'll go through those next time, but it turns out that you can do addition and subtraction in the derivative inside or outside as you want. Sort of the same thing as limits. And I guess, I can prove that if you like, but it's actually, I'll leave it up to you. It's kind of self-explanatory. This is going to be the sum from when I equals 0 to n of the derivative of a to the I times x, ai times x to the I. And then I guess I also didn't state this. We'll do a lot next time, but I sort of assumed it that I could take constants out of the derivative, which is a thing that you can do. So then this is going to be equal to the sum from when I equals 0 to n of ai times the derivative of x to the I. And then this is going to be the sum from when I equals 0 to n of ai times x to the I, not that. This is going to be I times x to the I minus 1. Okay, but then we need something here. This is actually not going to be from I equals 0, because we put I equals 0, we get 0. So I can actually just remove that and put a 1. So that's the derivative of any polynomial. And again, I sort of assumed a lot of things. First, that you can do addition and subtraction inside or outside the derivative. I'll make sure to state that properly next time. And also, you can take constants out of a derivative, just like you can a limit. I'll make sure to state that properly next time as well. But for today, that's the introduction to limits, and that is what we call the power rule, is that x to the n prime, this is another way of writing the derivative, is n times x to the n minus 1. So that's what we call power rule. It works for when n is not just a positive whole number, but we'll see the proof of that a little later. Yeah, so this is a good place to stop. Next time we'll be doing a lot. We'll be doing the product rule, chain rule, and quotient rule. So yeah, get ready for that. See you next time.